Hello and welcome to podcast.init, the podcast about Python and the people who make it great. I would like to thank everyone who supports the show on Patreon. Your contributions help to make the show sustainable. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at podcastinit.com/Linode and get a $20 credit to try out their fast and reliable Linux virtual servers for running your app. And now you can deliver your work to your users even faster with the newly upgraded 200 gigabit network in all of their data centers. If you're tired of cobbling together your deployment pipeline, then it's time to try out GoCD, the open source continuous delivery platform built by the people at ThoughtWorks who wrote the book about it. With GoCD, you get complete visibility into the life cycle of your software from one location. To download it now, go to podcastinit.com/GoCD. Professional support and enterprise plugins are available for added peace of mind. You can visit the site at podcastinit.com to subscribe to the show, sign up for the newsletter, and read the show notes. And if you have any questions, comments, or suggestions, I would love to hear them. You can reach me on Twitter at podcastinit or email me at hosts@podcastinit.com. To help other people find the show, please leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host, as usual, is Tobias Macey, and today I'm interviewing Jake Vanderplas about data science best practices and applying them to academic sciences. So, Jake, could you start by introducing yourself?
Yeah. So my name's Jake. I'm an astronomer by training, but for the last 5 or so years, I've been more on the data science side of academia. I've been working at the University of Washington eScience Institute, and we have a really a great team here and a really interesting goal, which has been for the last 5 years to kind of serve as a glue between all sorts of different scientific departments and other research departments on campus, with these common tools that everybody seems to be using, whether it's R or Python or machine learning algorithms or data cleaning approaches and things like this. So it's been a really fun position, and I've gotten to branch out a little bit from my astronomy into areas that I never imagined I'd be working on.
It's funny seeing the ways that your sort of progression through, particularly in technology, can change so drastically purely by the unifying fact that you're writing software.
Right. I sort of got into the Python world when I was doing my PhD in astronomy. And the reason was I was basically using NumPy and SciPy to drive everything I was doing with astronomy data. And it turns out that those tools are pretty general. So I started going to Python meetups and Python conferences and talking with people in other fields, and really got bitten by the open source bug and started contributing back to these packages. So that's sort of how I got into things here.
And what has been your experience sort of seeing the difference between the scientific Python communities and the more general Python communities, particularly as it manifests between the SciPy conferences and the PyCon series?
Yeah, so I've been going to these both conference series, SciPy and PyCon, since about 2012. And early on, they were very different conferences. When I started at PyCon, it was like there was not much science or data content in it. It was a lot of web development stuff, Django and a lot of the core Python contributions and having fun with generator expressions and things like that. Whereas the SciPy conference has always been about showcasing research that happens using Python, that's enabled by Python. But it seems like over the last 5 years, there's been kind of a convergence a little bit. Both conferences have moved a little closer together, and that they've both embraced data science to some extent. You go to SciPy and there are tutorials on pandas and doing large database queries with pandas style operations and things like this that are not necessarily all that close to the physical science roots of SciPy, but are more in the data science sense of things. And then on the other hand, you have PyCon, which has moved into that realm as well. I was in 2013, 2014, actually almost every year for the past 4 years, I've been involved with the tutorial evaluations and sometimes the tutorial selections for PyCon. And I remember in 2013, there was a discussion because among the committee, because there were like 3 data science tutorials that were submitted, or maybe like one on scikit-learn and one on machine learning with some other tool. And there's this discussion in the committee that like, should we really devote 2 tutorial sessions to such a niche topic like data science, right? And then it's just funny thinking back on that, because this last year, if you look at the PyCon tutorials in 2017, they were like half of them were data science, maybe 3/4 of them. So it's totally shifted over the last few years.
Yeah, it's definitely interesting seeing the ways that the massive amounts of data that are being collected now are so drastically influencing the career availabilities and the ways that some of the different popular languages are being used that weren't really being thought of at the time when they were first being created.
Yeah, and you see that larger trend too. Like 5 years ago, when Python was all about web stuff, it was, all the talk was whether Ruby on Rails is going to overtake what people are using Python for. Now you don't hear much about that, but you hear more about the R versus Python thing, or Julia versus Python in the sort of scientific numerics world.
Right. And then in the systems area, it's a lot of talk about Go versus Python, largely because of the packaging story and deployment.
Mm-hmm, mm-hmm.
And you mentioned that your background was originally in astronomy, and now you're working more in the data science and education space. I'm wondering how your background in astronomy informs and influences your current work.
Yeah, well, I still, fortunately, I still get to work on astronomy topics a little bit here and there. I've been publishing maybe one paper a year in astronomy journals, so I've kept my toes in there. But the thing is that astronomy, in a lot of ways, was kind of an early adopter of these really data-driven approaches to science. We had, even going back 15 years or so, with the start of the Sloan Digital Sky Survey, it was this mode of scientific operation where you basically, what Sloan did was it scanned the whole sky and got kind of this big catalog of objects up in the sky, and then went back and followed up on those objects with some detailed spectroscopic observations. And in the end, it's somewhere, I think, over the course of 10 years, they got a couple million of these spectroscopic observations. And the idea there was that this was really revolutionary at the time. The idea was that if you wanted to be an astronomer studying the sky, instead of doing the classic thing of going out and applying for telescope time and then pointing that telescope where you want and then getting that data, they wanted the mode of exploring the sky to be database queries, right? You have this huge database, this huge catalog of all these interesting objects in the sky, and a public open database where you can query by position, by object type, by all sorts of different data sets. So astronomy has been doing this thing for a long time, and I feel like in some ways the last 5 years of you might call it a data science revolution in scientific research, it's been a lot of other fields catching up to that notion of large public data sets, of working together in kind of an open fashion. And it's been really fun to see. And to be honest, astronomy has prepared me really well for that.
And in your current work at the University of Washington, you're working on educating students on some of the different best practices in data science. And my understanding as well is that you're teaching some of those same lessons.
Yeah, what we're doing at eScience is sort of multi-pronged. We're trying to reach all of campus, right? Because there's of course students that need to learn these skills to be effective scientists in this era. And so one of the things we've done on the education side that's been interesting is we've been trying to influence the curricula of all these departments around campus. And as you can imagine, if you've ever been in academia, you know that it's hard to change things. There's a lot of inertia. And if you say, for example, that you think astronomers need to be learning about how to work with large data sets, how to write effective code, how to do software engineering, that sort of thing. And you say, okay, well, let's create a graduate class for that. But graduate students are already overworked and they already have a full curriculum. So if you're going to create a class that's about data science methods, about software engineering, about statistical methods, or something like that, you need to figure out what you're going to drop from their curriculum, right? And this is really hard because what are you going to drop? Stellar atmospheres? Are you going to drop the course on the interstellar dust? Because each of those courses has someone who has devoted their career to studying this thing and thinks it's the most important thing in the world. So how could you get a PhD in astronomy without having a course in that? So it's this really difficult thing, right? Because it's this set of skills that's absolutely fundamental to doing science today. And departments are really slow to actually add that to the curriculum. So we've been pushing on that in a number of different ways here and giving graduate students these interdisciplinary electives that they can take, things like transcriptable options where you could, if you take these extra courses, you could get a PhD in biology with an emphasis in data science. And that appears on your transcript, kind of like a minor for an undergraduate degree. So we've been working with the administration, working with different departments to try to figure out how to get these sorts of skills into the main curricula. But at the same time, we've been doing a lot on the more informal education side. So programs like software carpentry have been amazing. We've been a partner with Software Carpentry for a number of years now and running workshops a few times a quarter. And that's just to get, if you're not familiar with software carpentry, that basically takes people from ground zero to figuring out how to use the shell, how to work with Python or with R, how to manipulate data, how to use Git and GitHub and version control, and these sorts of core skills that are so necessary these days in science. Another aspect of it that's been really fun is not so much working with the students, but working with the researchers that are already in place, whether they're postdocs or research scientists or even faculty. And we have a number of ways through the eScience Institute where we can build connections with people around campus. And they go from really simple things like just having open office hours. We have one of our eScience data scientists or research scientists is basically on duty all through the week. Each person does about 2 hours or so. And so throughout the week, anyone from around campus can come in and just ask technical questions about their research and get connected with someone who has expertise in the area they need, whether they need some sort of statistical modeling or whether they need to apply machine learning in some way or whether they need to scale up their data and use databases effectively or whether they need to build a web front end for some kind of public outreach aspect of their research. So we have all these ways of connecting with people around campus. And then for me as an academic researcher, those have often led to more long-term collaborations. So now I have, instead of just having papers in astronomy, I have papers in geophysics or in transportation policy or things like that. And it's been really fun.
And in the work that you're doing, both with students and with active researchers, what have been some of the common misconceptions or stumbling blocks that they come across in the process of trying to learn and understand and apply these different statistical and data science techniques?
So it really varies from person to person because we get there's a lot of people who have there's a wide range of backgrounds when it comes to computing and to statistics. And it's because these topics are not treated in a lot of undergraduate and graduate curricula. These topics are not treated as first-class citizens. So there's a huge range of what people know coming in. But the biggest challenge, actually, as far as academic research goes, is that the incentive structure for academics, if people are looking to basically get tenure eventually, the incentive structure has nothing to do with writing good code or writing good tools that other people can make use of. It's all about papers and citations, right? So if I tell someone, hey, you'll be much better in the long run if you can version control your code and document the code and write it in a modular way so that the next time you come around, you can remember what you did and build on what you did. That doesn't help someone get a paper out in the next month that they need in order to to appease their tenure committee, right? So academia is in this weird place right now where it's kind of, in some ways, shot itself in the foot by developing these incentive structures that don't match what makes research most effective in the long run. So a big part of what we've been doing here and what we've been working on with our colleagues at NYU and Berkeley, who are on who we share a grant with, is trying to figure out how to nudge academia in the right direction and think about how we can make it so that the activities we think are valuable to science overall are recognized within the incentive structure. They're recognized by hiring committees, recognized by funding committees, so that if I spend a week or two after publishing a paper making sure that my software is something that can be used by other researchers to reproduce my results, to extend my results, or to make their own research more effective, it's important to make sure that that's somehow recognized. Or if it's not recognized, then it's a waste of 2 weeks in terms of my academic career, even though it might be incredibly valuable in terms of the progress of science as a whole.
Given the fact that there are all of these different tools and technologies and techniques that would benefit the researchers in the long run, and a lot of them have a fairly steep learning curve, what are some of the areas of improvement, particularly in that tooling, that you think would be most beneficial, particularly to the academic sciences?
Yeah, that's a good question, because there are a lot of barriers to entry and there's pretty steep learning curves. One thing that we teach often is Git for version control. And Git it can be just so painful because there's so many things to remember. There's this whole mental model of what's going on with your repository and the remote and the staging area and the commit history and the directory, and it takes a long time sometimes to get someone familiar enough where Git is a tool that helps their workflow rather than hinders their workflow. So that's something that's pretty hard. I think it's sort of unfortunate that we as a data science community have landed on Git and GitHub, because I think Mercurial has a lot of the advantages of Git and makes things a little bit easier. But we've ended up in this place where Git is sort of the lingua franca of code development, of open source development, and of reproducibility. So we have to teach that if we want people to be able to work with that. So those sorts of things. And then there are other things too, like in the Python world, the plotting thing. Visualization is not all that easy. Matplotlib is a really incredible tool because it allows you to do almost anything you want as far as creating publication quality graphics. But it's not all that great a tool for like quick exploratory visualization. You end up needing to do a lot of tweaking of axes and figure layouts and things like this that impede your ability to quickly explore data. So those kind of things are difficult, and there's I think there are efforts on various fronts to make these tools easier to use. The other thing I wanted to mention along that, the difficulties that academics have, is the packaging and installation and remembering, like for Python, for example, remembering the difference between Unix paths and Python paths and Jupyter kernels and where they're pointing and all this sort of stuff sometimes means that, if a student comes up to me and is using a Jupyter notebook and says, I want to install AstroPy so I can use it in this notebook, there's like this whole backtrack we need to do of like, what kernel are you using? What Python version are you using? Are you using pip or conda? And how do you use pip or conda and to install it in that specific environment? There's conda ends and there's virtual ends and all this sort of stuff. Like, if you take a little while to explain it and figure it out, it all makes sense. But for a new grad student coming in who just wants to run some Python code, it's the startup cost is pretty immense. So I think fundamentally what's going on there is you have tools written by sort of Linux hackers for Linux hackers, and then now you have people coming along who have only ever double clicked on icons and windows that want to use this, and there's kind of a lack of common experience and common knowledge by the people who design the API versus the users, and that's a real challenge. So it means that to start using these tools, you need to get people up to speed on using the Unix command line, which doesn't always feel like the best use of time for someone who's worried about funding next month and trying to get research out. So it can be a little bit difficult.
Yeah, the Unix command line in particular is a long road to go down because I use it every day for my work as a systems administrator, and there are still things that are obtuse and sort of unintuitive for me and for people who have been doing it even for longer than I have, because it's just a sort of amalgamation of different tools with a little bit of glue to bind them together. So it's interesting to see efforts such as the conch shell from Anthony Skopatz and how that can potentially play into trying to ease that on-ramp for people who want to be able to work in this environment but not get exposed to some of the sharp edges of the overall Unix ecosystem.
Yeah, and there've been other. I like that you mentioned the conch shell. That's a really, really nice project, and it streamlines some of those things. Other examples, I think, of people that are trying to smooth over those rough edges are the Jupyter project. Bringing everything through these notebooks or through this new Jupyter Lab interface to sort of hide the details of what are happening for beginners. And then also the Conda project, I think, has been really valuable because it lets people, it takes away some of the installation headaches that dominated the Python world in the 2000s. If you tried to install SciPy from source, even on Linux in like 2005, it was a pain in the butt. Now you can, even if you're on Windows or Mac, you can type conda install SciPy and you basically have it working. But one of the problems with that I've been noticing in my teaching is that every time you create a new tool or a new layer that smooths out the rough edges of the layer below it, it means that everything works well 95% of the time, but the 5% of the time it breaks, your user has absolutely no vocabulary to figure out how to fix it. So the example that comes to mind is if you have a user using a Jupyter notebook, and I mentioned this before. If you're in a Jupyter notebook and you want to install SciPy so that it works in your Jupyter notebook, you need to know that the Jupyter notebook has these kernels that are running in under it, and the kernel points to a Python environment, and a Python environment is built by virtualenv or by conda, and in order to install in that environment, you need to choose which installer to use, whether it's pip or conda install, and you need to make sure the environment is activated before you run it, and that the pip that you're using points to the Python version that you're using in the Jupyter kernel. So there's this whole level of abstraction that you don't want people to worry about, and they usually don't. But then when something goes wrong, they're all of a sudden confronted with this tidal wave of concepts that they need to know in order to just get SciPy working in their notebook, right? And I see that with a lot of these tools that are trying to smooth things over. And I debate what to do about that, right? Because on one hand, you could go the route of let's just start with the command line and let's ignore all these tools so that we build up the knowledge people need in order to debug everything that comes up. But then you spend 10 weeks getting people to the point where they can run, print hello world in a conda environment or something, right? But on the other hand, if you try to smooth out all of those and get people working with their hands on data right away, maybe using a VM that's set up perfectly to run Jupyter Notebook that they connect to over the network, and nothing's running on their own computer. You can do that and you can get them analyzing data right away. But then at the end of the quarter, when that VM server turns off, they are no further along than they were at the beginning because they don't know how to use their computer. So this is the kind of question that I really have been struggling with lately, is in terms of data science education, is what level of abstraction do you start with the students, and how much do you spend time teaching fundamentals like how to list directories in the Unix shell, and how much do you spend time relegating those questions to Stack Overflow and teaching them how to manipulate and visualize data? And it's a hard one.
The layers of abstraction problem has been plaguing software since there was software, basically. So, there's the law of leaky abstractions, where every abstraction will leak at some point,
right.
And it's great until it isn't, and then it's horrible.
We should all just be writing machine code, right?
One of the projects that you're involved with right now is Altair, which you were mentioning some of the difficulties of being able to work with interactive visualizations, particularly in the context of Matplotlib. And my understanding is that Altair is an effort in that direction for being able to generate statistical visualizations with a strong integration with Pandas data frames. So I'm curious how the work that you're doing on that factors into your teaching, and what are some of your goals with that project overall?
Yeah, this project has been really interesting because on my side, it's kind of a software engineering challenge, and all the conceptual parts of it are sort of taken care of and baked in. So it's based on this visualization grammar called Vega Lite that comes out of the Interactive Data Lab here at University of Washington. And that lab is run by Jeff Hare. You may have heard of Jeff Hare because he and his grad student, when he was at Stanford, he and his grad student, Mike Bostock, created this thing called D3, which drives a lot of interactive visualization on the web these days. But if you have ever tried to use D3 in a exploratory data analysis context, it's really painful, right? Because D3 is this incredibly imperative thing. You're like drawing the axis and then drawing the tick marks and then drawing the data. And to create a bar chart in D3, it's like 100 lines of code or something like that. So D3 is awesome for these kind of polished, finished products and making something that's available to the world through this web API. But it's not great for the exploratory process. And so when Jeff finished D3, he started working on these grammars of visualization that would kind of address that. So Vega is a declarative grammar of visualization that lets you say, instead of here's some code to draw the axis, and then here's some code to draw some dots in the right place on those axes to visualize, create a scatter plot. Instead, what Vega does is it says here's the data, and here's how I want the data to be visualized on the screen. It gives you a grammar to specify that. Vega itself is still a little bit complicated. So after Vega was more or less complete, the team started working on Vega Lite. And the idea of Vega Lite is pretty cool. You're basically taking these concepts that have come out of the data visualization research over the past few years and creating a grammar that lets you express those concepts. So for example, if you want to scatter plot some data on X versus Y, really fundamentally what you're doing is you're taking a column of data and mapping it to the X-axis on the chart. And you're taking another column of data and you're mapping it to the Y-axis on the chart. And then the charting library should, once given that, should be able to generate the points and generate the axis and all these things. So all you really need to specify is, here's some data. I want X to be this column. I want Y to be that column. And then the details are taken care of. So it's a really powerful way to quickly visualize data, because you don't have to worry about all these incidental details. And what the Altair project does is it creates a Python API around this grammar of visualization. The grammar is expressed in the form of JSON notation. And I don't like writing raw JSON dictionaries. So I'd rather use some sort of object-oriented API in Python that generates those JSON structures. So that's what Altair tries to do. And it's been a really fun project because it allows you to really quickly build up complicated visualizations from these core fundamental concepts. And what I'm really excited about Altair for data science education is the fact that number one, it takes away the need to learn this very imperative boilerplate that you get in something like Matplotlib, and lets you basically just think conceptually about the data and the visualization. And also by design, it enforces visualization best practices in some ways, because you're not in an imperative language where you're building the plot element by element to the final piece. you have to think at each element, is this a good choice as far as what we know about effective data visualization? But in the case of Altair and Vega Lite, those good choices are being made by the code behind the declarative specification. So you end up with really useful visualizations without having to think about the details of that along the way. So my colleague Brian Granger, who's on the Jupyter team, and he teaches down at Cal Poly San Luis Obispo. He's been using our early versions of Altair to teach data science and teach like the fundamentals of data visualization. And it seems like it's been pretty successful for him because the API of the library kind of shifts how you think about data visualization. So you're thinking in terms of things like encoding, like mapping columns to channels, to encoding channels and visualization channels, and these things that help you make visualizations more effectively no matter what tool you're using. So it's sort of like when the API mirrors best practice, you end up in a much better situation.
And one of the utilities of data visualization in the context of doing data science is being able to quickly identify what the overall shape of the data is, identify outliers visually rather than having to painstakingly go through the underlying data or perform statistical analyses on the data that may or may not yield any useful results, and then being able to guide the direction in which you are querying the data and trying to process it to see what are some of the underlying answers that you can gain from it. So I can definitely see how having Altair as a quick way of translating the data from the format that you already have it in your Python code to a format that you can see visually will drastically increase the rate at which people can explore and process that underlying data.
We still do have a few technical challenges in it that we're working out. Like, for example, the fact that the Python code spits out this JavaScript notation that's then read by the JavaScript Vega Lite library in order to visualize it in your browser. Because there are these multiple steps, right? It's another layer of abstraction, right? And we run into issues where if there's an error on the Python side, we know how to handle that. But if there's an error on the JavaScript side, it's sometimes hard for users to debug. The initial release of Altair, if you did something wrong, like if you specified a column that doesn't exist in your data, the output would just be blank, right? And it gives you no hint about the fact that you used a capital letter versus a lowercase letter in your column name. So we're still working through some of the usability issues of that. The other thing is that the mode that it works in, if you have a pandas data frame, is it serializes the data frame to JSON and then passes that whole JSON object to the browser in order to visualize. So if you have a data frame with 1 million elements, then what it tries to do is serialize a million rows into JSON, and you end up with this massive glob of data that you're submitting to your browser, and it can make things run pretty slowly. So we're still, I'd say the library is still young, and we're trying to iron out some of these issues that come up. But I think long term, as we work with this library with students and kind of figure out how to streamline some of those things and make the errors easier to recover from, I think it could be a really useful library.
And one of the other libraries that I'm familiar with that seems to be targeting a similar application is Bokeh from the folks at Continuum. So I'm wondering what was lacking or sort of difficult in that library that necessitated the work on Altair, or are they just targeting completely different use cases?
Yeah, that's an interesting one because Bokeh started out 5 years ago. They really wanted to do kind of like a ggplot style thing for Python. I know Peter Wang, when he was starting Bokeh, he really was he was digging into grammar of graphics and figuring out how to do those sorts of things in a more declarative manner. As Bokeh developed, it became kind of more of an imperative engine that they wanted to build a declarative wrapper on later on. So if you use Bokeh, it's an incredible library. You can do these these amazing interactive visualizations online. You can target the browser. You can even do really large data sets because they use HTML5 canvas rather than SVG. So it allows you to do some bigger data sets than other web visualization tools. The thing that was lacking for me was the easy API. Bokeh to do a lot of things requires a lot of boilerplate code in general, in my experience. And I know people might get mad at me for saying that, but I just don't find it all that more intuitive than a tool like Matplotlib for your daily exploratory data analysis. That said, they have been working on this recently. There's a package called HoloViews that started out as a separate visualization package, and it's now been wrapped into the Bokeh project, and it's going to basically be Bokeh's declarative API. So it's sort of the exploratory data analysis or data visualization API built on top of this really powerful backend that's the Bokeh library. I think I see a lot of potential there. I think that could be a really nice tool as time goes on. With Altair, we have a slightly different goal than Bokeh's goal. We want it to be an API that people can use, but key part of Altair is this Vega Lite backend. And Vega Lite is more than just an API for visualization. It's a grammar of graphics serialization. So the idea is that if you create a plot in Altair, you can serialize it to Vega Lite. And Vega Lite is this compact JSON notation that you can pass to anyone that in principle tells you everything you need to know to reproduce the plot. So my vision long-term, what I would love to have is a Matplotlib reader for Vega Lite. So you can create something in Altair, send it to Matplotlib, load it up in Matplotlib, and then start doing Matplotlib's annotations on top of it. Similarly, I could imagine sending this Vega Lite thing over to Bokeh or sending it over to ggplot, and having Vega Lite be this sort of lingua franca that operates between programming languages and between packages in those languages. Now that vision will take a long time and a lot of software engineering to realize, but we're seeing a little bit of this buy-in. Like for example, Wikimedia recognizes Vega Lite for visualizations now. So you can go on Wikimedia and put a Vega Lite specification in there and it will render it on the web page. And then if someone comes along and they want to modify that plot, they're not trying to reproduce someone's PNG with another package in order to add a new axis label, right? They can actually load the Vega Lite and change the Vega Lite spec using a raw JSON editor. They could change it using a tool like Altair, or in the future, you might be able to change it with a tool like Bokeh or ggplot or Matplotlib or HoloViews or any of these other ones. So our vision for that is to really unify the visualization of information across languages and using this Vega Lite as a format. I should mention similarly that in the newer versions of Jupyter Notebook, Vega Lite is built in. So, you no longer will have to load the Vega Lite library. Jupyter just knows how to handle Vega Lite. So whether you're using Jupyter from R, from Python, from Julia, if you have a visualization library that knows how to output these serializations, these Vega Lite specifications, then you can visualize it in Jupyter. You can visualize it on Wikimedia, and we're hoping other tools will adopt that as well.
And it sounds like you've been involved in a lot of really interesting research and applications of data science. I'm wondering, what are some of the most novel or noteworthy that you think are worth mentioning here?
Yeah, so there have been a lot of interesting things. My work over the past few years has been more along the lines of like the software engineering side of things. So one of the things I really enjoy doing is taking algorithms and concepts that are kind of locked away in basically useless papers and putting them in the form of software so that I can use them in my projects and so that others can use them in theirs. And so I think this is a real strength of the kind of data science workflow that's the reproducible workflow that's going on now. So I've been involved, for example, in the AstroPy project, which is a community collection of astronomy routines written in Python and documented well, unit tested well, maintained well. And so it means that I can take algorithms that are out there in the literature that everybody has their own homegrown version of and create a really nice nicely implemented, nicely documented version of this in a Python package that then others can go out and use instead of wasting cycles reinventing the wheel in their research. So that in my personal work, that's been kind of the thing that I've been pretty passionate about is doing these sorts of things. From kind of colleagues around the world and in my institution, the one thing that I've been really excited about is seeing the uptake of tools like the Jupyter Notebook for publishing executable documents in association with scientific projects. And the best example of that from the last couple of years, I think, is the LIGO results, these gravitational wave results. And it's amazing now that, it's getting to the point that observing gravitational waves from a pair of colliding black holes is commonplace enough that it doesn't even get a press release anymore. There was one, I think, last week that sort of flew under the radar. But the team at LIGO is doing a great job of making the data available, making the simple analysis code available in the form of a Jupyter Notebook with explanations and with code inputs and outputs. So you, as average person on the internet with Jupyter installed, can go and download this and see how they did their analysis and see the statistics that go into extracting gravitational wave signals from this incredibly noisy data. And that sort of thing I think is amazing. We're seeing some of the same stuff in journalism as well. So some journalists have started taking when they're doing data-driven stories, they've started releasing that data and publishing Jupyter notebooks that allow you to go in and check their assumptions and make sure that what they're doing is up to par. So that sort of thing in the last 5-10 years has been 5 years, I should say. Jupyter Notebook's only about 5 years old, 6 years old. That sort of thing has been really cool to see. This ability of people to publish data, publish analysis scripts, and the average technically literate person on the internet can go in and check it and validate it.
Yeah, I think that's one of the really valuable and interesting outcomes of this revolution that we've been having in terms of data science and open data is the fact that it does lower the barrier for citizen scientists and to get involved, and also the advent of some of the more open journals that are making it easier to gain access to some of these publications and just have somebody who's not necessarily working in academia be able to actually double check some of those results and get involved in the overall scientific process rather than having it be contained within these different universities or research institutions that have historically been harder to gain access to the common layperson.
It's been really cool to see that and to see it enabled by Python tools and enabled by some of the software that my friends and colleagues are spending their time on. It's great to see that impact in the real world.
And on those lines, what are some of the other trends in data science and data analysis that you're most excited for and seeing how they play out in the future?
I've already touched on some of the things that I'm most excited about is these. I mentioned the visualization, like the Altair specification being this lingua franca between languages. I think it's exciting to see that developing in other spaces too. Like, for example, Wes McKinney, who created Pandas, seems to be spending a lot of time recently on this sort of idea of translatable data structures in the case of data frames. There's this feather format that both Python and R can read, and these kinds of ideas. I think what I want to see in the next couple of years is people stop having these language wars. I think it might be fun, but it's very unfruitful to argue about R versus Python versus whatever other tool you want. These tools are all really great and have their advantages and disadvantages. And if we can make the tools work together, work in concert more easily, then I think we all win. Whereas if we spend our effort trying to troll our users on Twitter or something like that, then it's not as useful. So that's sort of a more ecumenical approach to data science, I think, is something I'm really excited about seeing.
Yeah, I can definitely agree with the fact that turning the conversation from either or to yes and can have much more valuable outcomes and fosters the growth of larger communities than just the ones that are contained within a particular language or tool set.
Yeah, definitely.
And are there any other topics that you think we should talk about that we didn't touch on yet?
Oh man, we covered all the stuff that I'm really excited about right now in the data science space.
Yeah, I think the one thing that we didn't really cover, because it deserves its own conversation in and of itself, is the idea of repeatability within research. But as I said, that's a very long and involved topic that does not have any obvious solutions yet. But I think that a lot of the work that you and others are doing in the tooling and sort of pedagogical techniques is sort of yielding fruit there to make it easier for that reproducibility of research.
Yeah, the combination of executable document formats like Jupyter Notebook and R Markdown, with building of software skills and the use of version control and open publishing of code, I think that's really addressing that. One thing that hasn't been really well addressed in that space, I think, is reproducibility and repeatability on the scale of like 5 to 10 years versus the scale of 6 months to 1 year. This is something I think we as scientists are going to have to address because packages evolve quickly, right? So a package like NumPy, you can do a lot of things in it, and if you install NumPy version 1.11, you can expect that you'll be able to do the same thing 10 years down the road. But features are deprecated, APIs are changed slowly over the course of years, and there are deprecation cycles so that, if you move from NumPy 1.11 to 1.13, maybe something that's going to be deprecated, there you get a warning and you can fix it. But code that's just sitting in a repository for a decade, I have no confidence that I'll be able to run that code again when I revisit it in 10 years. And that's a larger thing. And that goes beyond the packages. Even if you're able to record package versions and install legacy versions of Python and NumPy and the whole tool chain, like things like VMs or Docker containers even are what you build that on top of. Your foundation is shifting enough that I'm not sure we'd be able to work with it. So that's a concern to me because we're making such progress in the reproducibility space right now on the 1 to 3 year timeline that I think we're going to be grappling with the reproducibility issue on the 5 to 10 year timeline down the road.
Yeah, and even to just the challenges of data preservation, particularly with these large data sets, is where do you store it? Who pays for it?
Oh, yeah.
It's a very complicated discussion and maybe one that we can find time for on another episode.
Yeah. Well, the Moore's Law helps with that a little bit. I talked about the Sloan Digital Sky Survey. That was huge 15 years ago, but it's 20 terabytes now, which you can buy for a few $100s. Yeah, so we're getting there.
Well, I think this is probably a good place to wrap up. So for anybody who wants to get in touch with you or follow the work that you're up to, I'll have you add your preferred contact information to the show notes. And with that, I'll move us on to the picks.
Okay.
And my pick this week is going to be the Redwall Cookbook, which is just what it sounds like. For anybody who's not familiar with the Redwall series, they're this collection of novels that are focused around this group of woodland creatures that have built an abbey and all of the different adventures that they go on or enemies that they have to battle. It's a really fun and interesting set of novels, and every one of them has a description of these vast and ornate feasts with very detailed discussions of the types of food. And so for a long time, readers of the series were asking for a cookbook, and so the author of that series eventually did release one that is also a story in and of itself that has the recipes interspersed throughout. So it's a really fun book with some good recipes, and so I'll add a link to that in the show notes. And with that, cool. I'll pass it to you, Jake. Do you have any picks for us this week?
Oh man, what I've been reading recently is a lot of nonfiction, and there's a historian from Princeton named Kevin Kruse, who I really, really appreciate his. He wrote a book called White Flight, and then the other one, I'm reading the next one right now, and I'm trying to remember what it's called. But yeah, he has some really great perspectives on how social trends over the last 100 years have influenced the political landscape of today. And in light of what's going on in politics right now, I'm finding it really interesting to have that sort of historical
Definitely sounds like an interesting book. Well, I appreciate you taking the time out of your day today to join me and talk about the work that you're up to. It's definitely interesting and valuable endeavors, and I hope to continue following your work because you've already produced a lot of useful tools for myself and others. And so with that, I'd like to thank you again, and I hope you enjoy the rest of your day.
Yeah, thanks so much.